Okay, so in the last class we are looking at the meaning of Lagrange multiplier. Okay, so first we looked at the meaning of the Lagrange multiplier U or V. So U star V star means the value at the optima. Okay, star means the value at the optima. So basically, this U or V star represents the change of objective function due to unit positive change of constraint boundary B at the optima point X star. So we also found the explanation why U is negative for minimization problems, because in the minimization problems for unit positive change in the constraint boundary, the value of objective function decreases. Okay, from 30 it has reduced to 20. So this is why you should get negative values of U in minimization problems. And if you do maximization problem with Lagrange multiplier, then the value of U will be positive, because for unit positive change in the constraint boundary, the objective function value has changed from say 10 to 20, it has increased. So this is one feature of the Lagrangian function. Another property of the Lagrange multiplier is that at optima X star, the gradient vector of the objective function is a linear combination of the gradient vectors of the constraint. And the Lagrange multipliers U star are the scalar multipliers. So you can see that this is the gradient vector of the objective function. This is the gradient vector of the first constraint at the optima, that is at the contour of the optima. Then this is the gradient vector of the second constraint at the optima. And this U1 and U2 are the scalar multipliers. So when you multiply this del of G1 with U1 and del of G2 with U2, then that combination will give del of O. So let us see the graphical representation of this. Okay, so this is just for your mathematical understanding. Okay, it's not required for solving the problems. Okay, so this is the contour of the objective function. This green dot is the optima. Green dot is the optima. This is the contour of the objective function. So this del f is the gradient vector of the objective function at the optima. So what you have to do is that you have to draw this tangent passing through the optima, and then normal to the tangent will give gradient vector of the objective function at the optima. Okay, then del of G1 is the gradient vector of constraint 1. Okay, so it is normal to the what to say, the constraint boundary of G1. Then del of G2 is the gradient vector of the G2. So it is normal to the constraint boundary of G2. So you can, so this del G1 into U1 plus del G2 into U2 will give del into F. Okay, so U1 and U2 are the scalar multipliers of del G1 and del G2, which will give del of F. So this is the geometrical interpretation. Okay, so what is the purpose of this equation? Okay, the purpose of this equation is that the optimization algorithm can, at the end of the run, they can cross-check the value of U1 and U2 by substituting it into this equation and seeing that you get the value of del F. So you can calculate the value of del G1 and del G2 at the optima. We multiply this with U1 multiply this with U2 and you should get del F correctly. So with this we can check the values of U1 and U2. Okay, so that is, so now we go to the last topic of this Lagrange multipliers, that is Lagrange multiplier method without slack variable. Okay, so if you are an expert in optimization, you don't need to use the slack variable as S squared to decide if the constraint is if the variables, if the solution is satisfying the constraint. That is, if it's in the feasible region or infeasible region or in the active boundary. It is not required if you are expert. So let us see method without slack variable. The alternate form of KKT condition without the slack variable S squared. So in this method, we straight away write Uj into Gj. So there is no Gj plus S squared. So this term is not there. So S squared is not used anywhere. So you just write Uj into Gj for inequality constraint and Vi into Hi for equality constraint. The S squared term does not occur at all. So how do you use this approach? So now the four conditions are like this. So first of all, you have to equate del of L is equal to 0 like the previous method. So but only use this derivatives. Okay, that is partial L by partial x equal to 0, partial L by partial y equal to 0. Only design variable derivatives are used. Okay, so there is no need to find derivatives with respect to u and v. Okay, that's not required. Instead, you have to separately ensure that the constraint hi equal to 0 and gj of x is less than or equal to 0 is satisfied. So you have to substitute the xy value in these two equations and check that these constraints are satisfied. There is no need to find S squared and then check if S squared is negative or it's 0 or positive. That is not required. Instead, you directly substitute whatever xy value, whatever x star, y star value you get from these two equations. You directly substitute an equality constraint and check if it is satisfied. You directly substitute the inequality constraint and check if it is satisfied. Okay, then switching conditions are now represented by Uj into Gj is equal to 0. Okay. Or U is equal to 0 or the constraint is equal to 0. U equal to 0 means inactive. If G is equal to 0 means active. So you have to try these two switching conditions. There is no S is equal to 0. That is not there. And then thirdly, important thing is that U value should be negative. All U values should be negative. Okay. So let us do one simple problem with this. That is without using S squared. Use the alternate KKT conditions to find the minima of this objective function, subject to one equality constraint and one inequality constraint. So without using S squared. Okay, so you can write the Lagrangian like this. There is no S1 squared, S2 squared here. Okay. Okay, so previously we wrote a plus S squared, no? X squared plus Y squared minus 26 plus S squared is written. That is not written there. Okay. So this is the simple form without S squared. Okay, so equality constraint H1, inequality constraint G1. So now we write all the KKT conditions for at the optima X star Y star. Okay, so for this, first you write partial L by partial X equal to 0, partial L by partial Y is equal to 0. Two conditions. Okay. Then you have to manually check that these two constraints are satisfied. That is, there is no S squared parameter to check. Okay, you have to manually check these are satisfied. Then this is the switching conditions. You have to start from here. Switching condition is for inequality condition. Okay, inequality constraint. Equality constraint is always active. There is no switching condition for equality constraint. So either U1 equal to 0 or this G1 equal to 0 or x squared plus y squared minus 26 is equal to 0. You have to try both of this. And lastly, the most important is sign condition. Sign of U must be negative. So let us start from switching condition and see what happens. Okay. So let us start with okay, U1 equal to 0. Okay, U1 equal to 0. So if you put U1 equal to 0, you get these type of equations. And okay, x star equal to minus 0.5. Okay. And U1 equal to minus 1. X star equal to minus 0.5. Okay. Okay, so does this value of x star satisfy the constraints? So one constraint is this. Okay, that is h1 equal to 0, this constraint. So you put 0.5 plus y minus 6 is equal to 0, y star equal to 6.5. So x star equal to minus 0.5, y star equal to 6.5 will satisfy the line constraint. So let us see if it will also satisfy this circle constraint. So you can see that it will not satisfy. Okay. Okay, because x squared plus y squared will give more than 26. Okay. 36 you will get. 6.5 squared, maybe 40 or something you will get. 40 minus 26 is positive value, so it is not less than 0. Okay, so the value of x and y you get from this condition, that is U1 equal to 0 will not satisfy this constraint. So in the previous method, we will calculate S1 squared and U1. Okay. And we'll check value of S1 squared. If S1 squared is negative or S1 squared is 0 or S1 squared is positive. That check is not there. Instead, you have to manually check that both these constraints are satisfied. Okay, so next we switch the other option. Then the constraint G1 is active, or x squared plus y squared minus 26 is equal to 0. And also equality constraint is active. Equality constraint is always active. So you have to solve these two things. Okay. So the value of x and y which satisfies the above two equation is x star is equal to 1 and y star is equal to 5. It satisfies the two constraints. And now you have to check the values of u and v. Okay, with this x star and y star. So you substitute this plus 1 and y is, this is plus 1, y is equal to plus 5. Okay, so you will get u star is equal to minus 3. So this is okay because u star must be negative. So u star is okay. V star is 7 by 3. The sign of V star does not matter. Okay, because the contours for equality constraint can come from any direction. Okay, so this is the right answer. Okay. So this type of simple hand calculation question will come in the exam. Okay, so one objective function and 2 or 3 constraints will be given. So with the Lagrange multiplier approach, you have to do the switching constraint and the switching operation, switching condition, and check which constraint is active and which constraint is inactive.
So this is also a part of this mid-sem exam.
No, that's only up to Fletcher-Reeve.
Okay,
Fletcher-Reeve method.
fine, sir. Thank you, sir.
This is all for second quiz.
Right, sir.
So this assignment I will give. After you submit first assignment, I will give second assignment with this Lagrange multiplier and calculation type of questions. Okay. So next we look into another topic, basic concept of discrete optimization. So this is very important for engineers, but unfortunately you can't do the hand calculation. Okay, you can only learn the algorithm, and it will be useful for you when you use this algorithm in MATLAB or something. Okay, so basic concept of discrete optimization. So what is discrete optimization? So in most engineering applications, design variables will be continuous, like length, breadth, and height are continuous variables. Okay, length you may get a 7.3 meter, width is equal to 2.1 meter, breadth is equal to 1.5 meter. So these are all continuous variables, or it will be decimals. So they gives smooth objective function which are differentiable. Standard methods like calculus methods like Cauchy's method or Fletcher-Reeve's method can be easily used for continuous variables. However, in some cases, variables may be binary. So the variable x can take values of 0 and 1 only. The variables may be integers, like the x may be the number of tables produced, okay, per week. So it can be only 1, 2, 3, 4, 5, 6, etc. It can't be 1.1 or 1.2, etc. So it may be integers. And then some of the variables may be discrete quantities, okay, like choosing standard gear module or standard bolt sizes. So gear modules may be like 2, 4, 6, 8, 10, etc. Okay. So you can only choose between these values. Okay. Then sometimes the problem may be a mixture of integer and continuous variables. So there may be two design variables, x and y. X can be only integer and y can be continuous. Okay, so mixed variables are there. So what to do for this type of problems? Actually, this type of problems will make it more difficult. That's what is the simple answer. Okay. So some people will always say you just solve the problem with continuous variables and you just round up the results. Okay, for example, okay, suppose x and y must be only integers. So what you do, you assume x and y to be continuous variables and you find the optima. Okay, suppose x star is equal to 7.7, y star is equal to 9.1. Okay, so then you just round it up to the nearby integer. So x is equal to 8 and y is equal to 9. So we will show that this will not work. Okay, this answer will be totally wrong if you round up the answer to the nearest integer. We'll see in the next slide. Okay, so consider the feasible region of a linear programming problem. So where x and y can take continuous values. Okay, so this is x, this is y, this is the feasible region of constraint 1. This is the feasible region of constraint 2. So this is the contour of objective function. Okay, so this is the solution, assuming that x and y are continuous. So the answer is x is equal to say 2.75 and y is equal to 3.4, assuming to be continuous variables. Okay. Okay, so now let us assume that x and y can have only integer values. So these blue dots are the integer values, and these blue dots represent the feasible region. Okay, for example, this integer is out of the feasible region, and this integer is out of the feasible region. The blue dots represent the feasible region. Okay, so this is the actual feasible region. If you allow x and y to have only integer values. So this is the optima assuming continuous solution. So now if you assume only assume that x and y can have only integer values, then this gray area is the feasible region and the contour will touch here. Okay, so the optima for x and y integer values is 1, 4. Okay, and the optima for continuous variable x and y is 2.75, 3.2. Now suppose we round this. Okay, suppose we are thinking that we find the optima using the continuous values of x and y, and we will just round up the solution. So you get 3, 3. Okay, so this is the rounded solution. Okay, but so actual solution for integer problem is 1, 4, and the solution you get by rounding up the continuous variable solution is 3, 3. Okay, 3, 3 versus 1, 4. There is a big difference. Okay, 3, 3 versus 1, 4. There is a big difference. So by simply rounding up the decimal values, you can't get the integer solution. Okay, various methods for discrete integer optimization. One is called cutting plane methods. Example is Gomori cutting plane method. So this is highly complicated. We are not going to look at this. So this is also highly approximate. So basic of this method is that by drawing various cutting lines like this, you approximate this feasible region. Okay. Obviously, some error will be here. These parts are all errors. Okay. So by this Gomori cut method, you can draw all these lines and try to reduce these areas. And so that in the end we get this feasible region. Okay. So successively, this method will successively make many cuts to the continuous feasible region to approximate the integer region. So this is an approximate method, sometimes not effective. So next, what we are going to look at branch and bound methods, which are accurate but a little more computationally intensive. So we are going to look at this method. So branch and bound methods, many algorithms are there. We look at Dawkins algorithm, which is the simplest one. Okay. So they systematically try out integer solution starting from the vicinity of the continuous solution. So the Dawkins algorithm also, first you have to find the continuous solution. Okay. First you have to assume x and y are continuous variables and find a solution, and that is the starting point for investigating the integers around that. Okay. Accurate results are obtained but require many iterations. Okay. Dawkins algorithm is illustrated for a linear programming problem. So maximize this objective function. Z equal to 8x1 plus 5x2. Okay. So various constraints are given. X1 and x2 are both non-negative integers. So how to solve this method? How to solve the solution? So first is you start with the continuous solution. So you assume x1, x2 are continuous variables. Okay, and You run the solution. So you get the first answer. X1 is equal to 3.75, y1, x2 is equal to 2.25. Okay. Okay, so next, what you have to do is that okay, let me wipe these things. Okay, what you have to do is that, so here both are variables. First, you force x1 to be an integer. Okay, while x2 is allowed to be an continuous variable. So first you force x1 to the nearest integer, and while x2 is allowed to be a continuous variable. So you can see the integer scale, okay, 3, 4. So x1 is now 3.75. Okay, x1 is now 3.75. So we want to investigate the integers 3 and below and 4 and above. This is for the variable x1. So 3 and below, 4 and above. Okay. So what you do is that you make 2 further linear programming problem. So here you give the constraint x1 is less than or equal to 3. X1 is less than or equal to 3, and another problem, x1 is greater than or equal to 4. Okay. And other constraints are same. So when you run this program, that is x1 is less than or equal to 3, you get the answer 3, 3. And when you run this program, x1 is greater than or equal to 4, you get the answer 4, 1.8. So since we are doing maximization, this has given better results. Okay, because this Z value is 41 is higher than 39. So we ignore this and we concentrate on this. So now you can look here carefully. X1 has become integer and x2 has become continuous. Okay. So x1 has become integer. So next we will try to make x1 also reach the we'll try to make x2 also reach the nearest integer. Okay, so let us look at, so this is x2. x2 is 1.8 now. Okay, so this is 1, this is 2. So x2 should be less than 1 and x2 should be greater than or equal to 2. Okay, we have to investigate these integer regions. Okay, so we write 2 linear programming problems. So here x2 is less than 1. Another is x2 is greater than 2. So when you solve these 2 problems, we find that this will give an error result. Okay. Okay. It will not go because the solution goes into the infeasible region, and this will give a result x1 equal to 4.44, x2 is equal to 1. Okay. So now x1 has become continuous. x2 has become integer. That is 1. Okay, x2 has become integer, x1 has become continuous, 4.44. So our effort now is to make x1 reach the nearest integer. So 4.44. Okay, so 4.44. So you give 2 limits for x1. x1 can be less than 4 or x1 can be greater than 5, because this is 4.44, this is 5, this is 4. So you have to investigate greater than 5 and less than 4. Okay, so x1 less than 4, x1 greater than 5. Okay, so Here we get the final solution because both are integers. Okay. And this z equal to 40 is more than z equal to 37. So when there is no further improvement, the solution will stop. So this is how you do the branch and bound method. So with the linear programming problem. Okay, so one more example is there from the Shom series. Okay. So some more answers, some more conclusions are there.
Sir, one thing, sir, for finding the intermediate value of x1 and x2,
Uh,
you have to just use the plotting graph, right? Like draw the feasible region, and at the corner
This is
points.
purely mathematical. No? There's no need for graph here. It is done with that at MATLAB LinProbe.
Okay.
MATLAB LinProbe you can use. No need to draw. Only thing that you have to call it again and again for each of these branches.
Okay. Got it, sir. Got it.
There's no need to draw.
Sir, I have one query. So suppose if x is between 4 and 5, so we are considering less than and equal to 4 and more than and equal to 5.
Right,
So
yeah.
why we are not considering between 4 and 5? Yes.
No, we already got between 4
Okay.
and 5. You will get same answer.
Oh, okay.
Already got 4.44, no?
Correct.
That is between 4 and 5. If you give that constant, you will get the same answer, 4.4.
Okay. Got it. Thank you.
Okay, then another thing. Okay, so no, so highly important answer is that. Note that the final solution is 50, and it is not at all the same as rounding up the initial continuous solution. That is 3.75, 2.25. Then you would have got 4.2. This 4.2 is totally different from 50. So simply by rounding up the initial continuous solution, you will not get the answer for the integer problem. Okay, then it is possible to replace integers with discrete values like bolt sizes or modules, and you can give constraints that x1 is less than 6 x1 is less than 6 and x2 is greater than 8. Okay, so you can deal with the discrete values also. And mixed variables are also easy. That x1 is integer, x2 is continuous. Okay. In fact, if it is mixed variables, we would have solved it much easier. So x1 is integer, x2 is continuous means we would have solved it here itself. Okay. In one step, it would have been solved here. Okay, then one further example we'll do and stop. Okay, this is also the same topic of integer variables. Okay, so maximize this objective function with two variables x and y and three constraints. Okay, 3 or 4 constraints, and x1 and x2 must be non-negative integers. So this is taken from Shom series. So it is written as a flow chart. They are not writing step by step. Okay, so first you find the maxima assuming both x and y are continuous variables. So you get x1 and x2 are continuous variables. x1 is 2.25, x2 is 1.5. Okay. Now, what you do is that you try to force x2 to the nearest integer. So x2 is 1.5. So 1.5 is between 1 and 2. Okay. So you give x2 less than 1. Okay. x2 less than 1. Investigate in this branch, and x2 greater than 2, investigate in this branch. So for one you get the objective function is 11.5, another you get 12.5. So 12.5 is more than 11.5. So you choose this answer. So now, okay, x2 has become an integer and x1 is continuous. So now you have to concentrate on forcing this x1 to reach the nearest integer. So x1 is less than 1 and x1 is greater than 2. Okay, that is on either side of 1.5. So this will give infeasible solution. This will give a solution 1 and 7/3. Okay. So you can see that this is non-integer. So, and x1 is integer. So we have to force 7/3 to reach the nearest integer. So 7/3 is between 2 and 3. So less than, or you give a constraint, x2 is less than or equal to 2 and x2 is greater than or equal to 3. So you get two solutions. So first is objective function is 11, another is objective function 12. So 12 is greater than 11 and also both have become integers. Okay. X1 is equal to 0 and y1 is equal to 3. So this is the stopping point. Okay. If you run again, you get you get the same solution here. Okay. Okay, we can stop here. Okay. I have to take attendance.